Well, in case I have a lot more material to cover. Okay, wait maybe a minute. Shall we start?
Yeah, okay, so let's get going. We can finish up. Leonardo Rastelli will tell us more about superconformal field theories as we leave the comforts of Lagrangians behind.
Oh, wow. Uncharted waters. So I promised in the first lecture to explain a few structural facts about superconformal field theories in general dimensions, and then, of course, I didn't get the chance to do it because I had a certain logical flow to follow. So let me take a few minutes now. So we have already seen the main structure of how we get superconformal multiplets, how we use them to derive structural properties, for example, about existence of exactly marginal deformation, existence of flavor global symmetries in the case of n equals to 2, and much of the same ideology carries over, of course, in general dimensions and for general amount of supersymmetries. And so let me, very briefly, without going to the detail, let me make some of these structural remarks. So for example, we could take 4-dimensional n equal to 4 supersymmetry, and there it turns out that the stress tensor is now in the same multiplet as the exactly marginal deformation. So unlike the case of n equals to 2, where they sit in separate multiplets, and so a priori, of course, we always have a unique stress tensor where we can have several exactly marginal deformations. Here the situation is such that if we insist that the theory has a unique stress tensor, as we should, otherwise it really means we're considering a trivial product of theories, then let me write this down, is in the same multiplet as the exactly marginal deformation. Just from this basic representation theoretic fact, we conclude that a simple n equal to 4 superconformal field theory has a one complex dimensional conformal manifold. Another structural fact that just follows from representation theory is that there simply are no global favored symmetries whatsoever. With the usual caveat that, yes, you can conserve spin 1 dimension 3 current, but only in multiplets that contain higher spin currents. So only at the free field point you can have enhanced global symmetry, but at the generic point of the conformal manifold, there simply are no multiplets that accommodate conserved currents. I should also parenthetically remark something about the n equal to 3 case, since this is new and exciting. So in the old days, there was a simple argument that said that n equal to 3 implies n equals to 4. Perhaps Clay reviewed it briefly. It just follows from the structure of on-shell representations. If you assume you have a free field content, you can just look at the structure of the on-shell multiple, and you see that if you impose CPT, n equal to 3 immediately implies n equals to 4. And so the n equal to 3 vector multiplet is necessarily an n equal to 4 vector multiplet. But this is not so at the level of abstract representation theory. In particular, the stress tensor multiple for n equal to 2, the n equal to 3 is distinct from the one of n equals to 4. And it has the feature of not containing an exactly marginal deformation. And furthermore, you can argue that a genuine n equal to 3 theory, a putative genuine n equal to 3 superconformal field theory, is such that there are no allowed exactly marginal deformations. Of course, you can always take an n equal to 4 theory regarding an n equal to 3 theory, and then the stress tensor multiplet will decompose accordingly. But the only way for an n equal to 3 theory to have an exactly marginal deformation is precisely that is secretly n equals to 4. So a genuine n equal to 3 theory has no exactly marginal deformations. And that, of course, is compatible with the fact that we cannot find that in free field theory. So n equal to 3 superconfirmability theory, if any such theory exists, must be an isolated theory. And so intrinsically strongly coupled theory, you cannot change the coupling and go to weak coupling. And also, you can also discuss the same story and find that there are no global symmetries for similar reasons. And in fact, n equal to 3 superconfirmability theory have been found. There are physical constructions that involve either string theoretic, F theoretic type constructions, where you look at various brane systems at some frozen strong coupling singularities, or more field theoretically, you perform a certain quotient, something called an S-fold of an n equal to 4 theory that gives you an n equal to 3 theory. Yes, there is a question. No, the U1 is part of the stress tensor multiple. It's an art symmetry. Global symmetry for me is something that commutes with the superconformal algebra. Of course, there's always art symmetries, but those are part of the superconformal algebra. Okay, so we can also use the statement that there are no global symmetries in n equals to 4 to argue that the only possibility for maximal supersymmetry is PSU2 to 4. You could try to extend it to SU2 to 4, but remember that the extension is central. So from the point of view of PSU2 to 4, which is the standard n equal 4 superalgebra, the central extension would be a global symmetry. But no such thing is possible. So this is not allowed, because no global symmetry. And then it's now a simple additional step to argue that n greater than 4 is not allowed. Because remember, when I discussed NUM theorem, I told you, well, there is this infinite sequence of algebras where n can be unbounded. Nothing in the proof of NUM theorem prevents n to be arbitrarily large. But if n were greater than 4, then I could always decompose this algebra in terms of n equal to 4 multiplets, and inevitably the art symmetry of the bigger theory, which is un, from the point of view of the SU4 art symmetry of the n equal to 4 theory, contain additional Fravor currents, and those are not allowed. A similar reasoning, so again for the same reason. A similar reasoning holds in 6 dimensions. So in 6 dimensions, we found that a priori we could have an infinite sequence of chiral n, 0 superconformal algebras. We wrote the super algebra in detail in the first lecture. But of course we believe that n stops at 2, and the reason is similar. You can argue again, 2, 0 superconformal algebra admits no exactly marginal multiplets. Let me call it this way. I mean, you know what I mean. There are no multiplets whose top component necessary to preserve supersymmetry can be interpreted as an exactly marginal deformation. And so, again, this explains why the 2, 0 theory is an intrinsically solving coupled theory, and it also explains why n has to be bounded by 2, because if I could get higher n from the point of view of the 2, 0 theory, I would have the additional art symmetry generator would be interpreted as global symmetries, and that's not allowed. It's also the case that in d equal to 3, we found infinite sequences of superalgebra that are allowed by NUM's theorem, but there the SQ is a little different. In fact, it's perfectly possible to write down superconformal field theories in 3 dimensions with arbitrarily high amount of supersymmetries, but those are free field theories. And the intuition here comes from the Weinberg-Witten theorem. Mark has discussed the helicity, and the helicity in the little group for massless representations in 4 dimension is U1, but in 3 dimension, the massless little group is just discrete, is Z2, and just distinguish Bose-Einstein fermions. And so the usual argument from Weinberg-Witten that helicity greater than 1 is incompatible with the existence of a local stress tensor simply does not apply in 3D because there's no helicity quantum number apart from the statistics. And so it is actually possible to have theory with arbitrarily high number of supercharges in d equal to 3, but the point is that the stress tensor multiplet for number of supercharges greater than 8 contains higher spin currents. And so yes, it's possible to have more than 8 supercharges, but the superconformal field theory is necessarily free. So for physical theories in 3D, n stops at 8. By the way, these arguments, some of them were known before, but this very nice systematic discussion can be found in this paper by Cordova, Intrigligator, and Dumitrescu. Okay, so it was a little quick, but so this illustrates the power of this abstract representation theoretic reasoning to derive fully non-perturbative statements about superconformal field theories in various dimensions. There's a lot more. This is just, you could start classifying, for example, the possible relevant deformation that preserve various amounts of supersymmetry, and from very little, which is the structure of supermultiplets, you get a lot. Okay, so if there are no questions, I'll move on. Okay, so now let's resume our main line of thought. So we finished yesterday with a discussion of the SU2 theory with 4 flavors, and I was drawing this thing, which is the fundamental domain of the theory if we treat the 4 mass parameters, which are dual to the Cartan of SO8, of the SO8 flavored symmetry, as different. This is the fundamental domain of the conformal manifold, the theory. And then I made a mistake because I wasn't looking at my note. I told you that this was the fundamental domain of gamma 0, 2. That's actually wrong. Everything I told you is correct except that I gave the wrong name. This actually happens to be the group called gamma 2. Gamma 2 is matrices A, B, C, D, which are congruent to the identity mod 2. But everything else I said was correct. There are 3 cusp points, which are 0, 1, and I infinity. Those correspond to 3 different weak coupling limits, which really are the same kind of Lagrangian, but with a permutation of the masses. These 3 different weakly coupled Lagrangian are related by relabeling the masses, and that corresponds to a triality transformation. And we gave a geometric interpretation of this fact by saying that we could interpret this fundamental domain for gamma 2 as the complex structure moduli of the 4 puncture sphere if we treat the 4th puncture as being distinct. And then the 3 degeneration, well, as familiar, we can fix 3 of the punctures using the SL2C conformal killing vectors, and the position of the 4 puncture is free, and the 3 limits in which the puncture collides corresponds to the 3 cusps. And from a conformal viewpoint, this, of course, the 3 generation limits corresponds to this pair of Pence decomposition. For example, in the limit in which 1 comes close to 2, that's how the surface will look like, where these tubes go all the way to infinity, and conformally are the same as punctures in this picture, where the tubes have been brought to finite distance. And so the 3 different the generation limits correspond to the three distinct pairs of pair decomposition of this point function sphere. And we further argued that that was actually, where should I write? How many blacks do I have here? Only two. Okay, well, here. That there was a more suggestive way to write the field content of the theory that made this structure of the conformal manifold more apparent. And the idea was to think of having splitting. So we remember how that went. We went from having QIA, I goes from 1 to 8, A from 1 to 2. This is the SO8 index, and this is the SU2 color index, color and flavor. So we said that we could think of this as an M tilde, sorry, I think I called it M, yes, it doesn't matter. M tilde and M double tilde indices, which are indices of two SO4s inside of SO8, and then we think of each of the SO4s as an SU2 times SU2. So lo and behold, we trade the field content for a pair of trifundamental half hypermultiplets, and then one index is gauged. And so we have this picture where each trifundamental half hypermultiplet corresponds to a trivalent node. The external labels here, A, B, D, E, are flavored symmetries, and the label C here is the gauged index. Okay? And then the three degeneration limits, or the surface, of course, map to ST, a new channel type of trivalent graph. Okay. So far so good. Now let's graduate to the next super QCD, which is SU3 with 6 hypers. Well, now the hypers are generally in a complex representation, so we cannot perform this game of regarding them as half hyper. So we have Q and Q tilde, where A 1, 2, 3 is the SU3 color index, and I 1 to 6 is the flavor index, the SU6 flavor. However, keep in mind the structure of the superpotential is phi A, B, Q, I, A, Q tilde, I, B. It's clear that I can rotate Q and Q tilde by a full-fledged U6. So the flavored symmetry also contains a U1 factor. Okay, so this is the flavored symmetry. Now, so let me write this again here. So we have U1 times SU6, the flavored symmetry. The most general theory of this kind, if you allow yourself for mass deformation, as we should in the context of Seiberg-Witten theory, will have then a set of mass deformations, one which is dual to the U1, and 3 which are dual to the Cartan of SU6. I discussed this abstractly the other time, but of course in this case we could just go ahead and write down explicit mass deformation and superpotentials, and by the time we diagonalize that matrix we would find that we can label the masses by the Cartans of the flavor group. And so from the solution of the theory that was found soon after, yes? the Cartan. Oh, sorry, the Cartan of SUC. It doesn't matter, but yes, you're right. Absolutely, I'm sorry. I was blanking. I was thinking about SU4. Yes. So we have this whole complicated set of massive formations, and soon after the work of Seiberg and Witten, some people, of course, did the next thing, which was to solve entirely for all the super QCD curves. And from the solution, so first of all, there is also, of course, a UV sorry, 2 pi. In the case of n equal to 2, it's more conventional to use this kind of slightly unusual parameterization where tau has periodicity 2. Sorry, has periodicity. Sorry, what am I doing? Here, this is what I want. Tau, the theta angle, of course, has always periodicity 2 pi, and so we use conventions where tau has periodicity 2. From the solution of the theory on the Coulomb branch, one finds a similar looking fundamental domain as I drew here, except that now if we treat all the masses as inequivalent, but we have learned our lesson, what we should be doing is really look at the duality group when we allow for certain transformations to act on the masses. Now here we don't have the beautiful SO8 triality that we had earlier, but it turns out that there is a duality symmetry that flips the sign of the singlet mass. Okay? So there are 2 weakly coupled limits of the theory that correspond to a Lagrangian SU3 theory with 6 flavor, and those are related by flipping the mass that is dual to the U1 flavored symmetry. And with this identification, then, the fundamental domain looks like this. It's a fundamental domain of gamma 02, hence my confusion yesterday, where gamma 02 is defined as this thing. Okay. So now this theory, even after taking into account this duality, which is the standard kind of S-duality that we have understood in the case of n equals to 4 pyramids and in the case of the SO8 theory, has 2 cusps. Has the cusps at I infinity and then the cusps at, well, either 1 or -1 because of this periodicity of tau. Okay. But now we are out of ideas. We're out of ideas because there's no relabeling of the masses that would allow us to interpret this point as having a weakly coupled gauge theory description. Okay, this is a truly strongly coupled point for which we have no conventional Lagrangian field theoretic interpretation. And in fact, from the solution of the theory, you can see that as you reach this weakly coupled cusp, at the generic point of the Coulomb branch, precisely 6 W bosons are becoming massless, and that's exactly what you need to reconstruct the SU3 gauge group. You remember, you always have the Cartan, the 2 U1s, at the generic point of the Coulomb branch. Those are always massless, and then as you reach weak coupling, the W bosons also become massless, you reconstruct the SU3 gauge group. Curiously, as you approach this point, you see that only 2 W bosons are becoming massless. So it looks like this theory wants to be interpreted as having a weakly coupled SU2 gauge group. Okay? So there is a weakly coupled, I mean potential, this is all rather suggestive at the moment. But then, I've given you now enough information that the way I've built up my story, that now there is really a compelling guess for what's going on here. Remember, I've kept drawing this funny picture of the conformal manifold. I told you, well, this cusps corresponds to point where we have enhanced hairspin symmetry to points where some gauge group is becoming weakly coupled. And I've also emphasized that it's very well possible to have isolated superconformal field theory with no Lagrangian description. So, okay, in this conformal manifold, this corresponds to SU3 and F equal to 6. It's a perfectly Lagrangian theory where, if you wish, the isolated superconformal field theory we're gauging is just a bunch of free hyperts. But generically on the conformal manifold, there could well be another point where what we are gauging is a more non-trivial superconformal field theory, which is not just a bunch of free hyperts. So the suggestion here is that this other funny point here corresponds to the gauging of some abstract building block, which is strongly coupled, and we are gauging with weakly gauged SU2. That is the proposal, which, with the benefit of hindsight, given how I build my story, it's basically the only thing you could possibly try to guess. But having gone this far, then we are basically done. Why are we basically done? Well, because I told you that in the conformal manifold there are a bunch of things that remain constant. One of them is the number and charge of the epsilon multiplets. The other is the flavored symmetry and the associated level K. And finally, the central charges A and C have to be constant. And so, well, that really puts extremely strong constraints of what this gadget should be, because we have to match all these gadgets. And in fact, on the Lagrangian side, we have epsilon 2 and epsilon 3, which are given by trace phi square and trace phi cube. On this mysterious side, well, I'm insisting that we have some SU2 gauge group, so there is some phi hat of this SU2, of this new SU2 gauge group. And then, since the number of epsilon multiple must match, necessarily the mysterious theory must contain an epsilon 3 multiplet and no other epsilon multiplets, because the content of epsilon multiplet must be constant on the conformal manifold. So this superconformal field theory must then be a rank 1 superconformal field theory with precisely one epsilon multiplet of charge 3. Well, but fortunately, we precisely have such a theory in the table that I had on the board the other time. So this then means that we should really identify this with the E6 rank 1 F theory, superconformal field theory. Or at least that's the proposal. Okay, let's try to see whether we can make it fly. Okay, so first of all, we are saying that we are gauging an SU2. So what that means is that we are choosing an SU2 subgroup of the full E6 flavored symmetry. Well, it turns out rather beautifully that there is a decomposition of E6. There's a composition of E6 that preserves an SU2 times SU6 covariant. Well, SU6 is great because we have SU6. This is the preserved group. If I gauge this subgroup of E6, I preserve the commutant, which is just SU6. And of course, we have SU6 flavored symmetry on the other side, so that's great news. But then we have to make sure that the gauging that we are doing is exactly marginal. And so we have to check that the one loop beta function coefficient is 0. And I went through great pain in giving you this abstract presentation of the vanishing of the beta function in terms of this abstractly defined level, K. And so we need to measure this K of the SU2 group that we are gauging inside E6. That requires a little calculation because as we embed SU2 into E6, we need to make sure that the normalization of the generators doesn't screw me up. Well, it turns out that in this case, the so-called embedding index is 1, meaning that if I take the E6 adjoint generators and I carve out this SU2 subgroup, the normalization is the canonical one. So the level of the SU2 subgroup is in fact the same as the level of the E6, because the embedding index of SU2 into E6 is 1. And that level was written in the table that I had the other day, and you can check in your notes that is actually equal to 6. Okay, so now HV here is HV of SU2, because that's the group that we want to gauge. And so what do we have? Well, we have 2 times 2 minus 6 times 2, and unfortunately, that doesn't work. But there's also something else that doesn't work, and it's the fact that the full flavored symmetry on the Lagrangian side, as I've emphasized, is not SU6, but is U6. So we are missing a U1 flavored symmetry. And there's a simple, in fact obvious, a unique way with the ingredients that we have to fix the problem, which is to declare that the superconformal field theory here that I have somewhere, well, never mind. The superconformal field theory that we are trying to gauge is not just the E6 theory, but in fact the direct sum of the E6 theory and a fundamental hyper. Okay, an hyper in the fundamental representation of the SU2, which is being gauged. Okay. There's really no other possibility because, first of all, it has to be a rank 0 theory because we don't want to augment the rank beyond 2. We already matched the rank of the theory. And so the only possibility for rank 0 is 3 hypers, and the only thing that has U1 flavored symmetry is a single hyper. If I have more than one, I will have a larger symmetry. Inside here, there's just a symmetry that rotates this Q and Q tilde by a phase. By the way, these Qs have nothing to do with the Qs that perhaps I should give hats to them. Right? So we have the elementary Qs in the original Lagrangian representation. This is a completely new set of hypermultiplets with an index A hat that corresponds to this other SU2 that emerges in this limit. And now we are in good shape because remember that the contribution to the beta function from a full hyper is C is 2 times C2 representation, which for the fundamental representation is 1. And so finally, with the -1 that comes from the hyper, we actually win. Okay? So that is the proposal. This other funny point comes from weak gauging of an SU2 of a theory which is the red sum of an E6 theory, and we are gauging a subgroup of that E6, and the fundamental hypermultiplets, which is in the fundamental of that SU2. And so we have matched, well, we have made some basic checks. The Coulomb branch now works. The central charge K works. You can go ahead and now check that the A and C central charges work in terms of the table that I gave you. And so it's already kind of an impressive set of checks, and we can make other more sophisticated shortly. Are there questions about this? So this is, of course, the duality that was found by Argyres and Seiberg in their famous paper. And what's really, okay, at the beginning when the paper appeared, it looked like an isolated curiosity, but in fact it contained a very fundamental lesson. And the very fundamental lesson is the one that I've emphasized throughout, that we should really think of these cusps in the conformal manifold as coming from weak gauging of some possibly isolated non-Lagrangian building blocks. And there's now by looking at, so this picture here. And by looking at a very vast class of examples, this is how it always works. All the singularities in all the conformal manifolds, all the theories that have been found, are always of this kind. As you reach the singularity, there's always some gauge group that is becoming weak, and you always find some, in the extreme limit, you always find some decoupled generalized matter, if you want to call it that way, which could contain some free hypers, but generally will be of this more generic type, where we could have an isolated superconformal field theory emerging at the cusp. And although there is no proof of this, this seems like a good thing to conjecture, that that's the general structure of the conformal manifold in n equal to 2 superconformal field theory, meaning the exact marginal deformations, the epsilon 2s, always come from weak gauging. You enumerate the number of epsilon 2, that's enumerating the number of exact marginal deformations, and what I'm conjecturing is that you will be able to find a direction in the conformal manifold where you will be able to interpret that particular complex direction that you have chosen in the extreme limit as coming from identifying that with the gauge coupling of some gauge group. So in other terms, the only way to get exact marginal deformation in equal to theories is by gauge couplings. Yes?
How you knew that an SU2 gauge group is emerging?
I mean, of course, it's a lot of hindsight, but that can be seen with, again, hindsight, and that's what Argyles and Seiber argued from the structure of the Seiber-Witten curve. You can see that there are pinching cycles as you approach that point, and there's not enough pinching cycles to reconstruct a full SU3, but there's just enough. As this cycle pinch, you have W balls are becoming light, and those you have just enough to reconstruct an SU2. Okay. So now we can play a similar game as we played for the SO8 theory, and give an interpretation of this moduli space in terms of a 4-puncture sphere, except that now this moduli space is the one that corresponds to a sphere where we treat 2 punctures as being equal to each other pairwise. Okay, so this is the complex moduli space of a sphere where we treat 2 punctures as identical and the other 2 as identical to each other, but not all 4 of them are identical. If we were treating all 4 of them as identical, I would go back to the SL2Z fundamental group. If I treat all 4 of them as distinct, is the gamma 2, and if I treat them this way, it's this moduli space. So the standard duality that flips the sign of the mass for the U1 is the duality that flips the identical punctures. That has already been taken into account the moment I'm treating these punctures as identical. Whereas the duality that corresponds to the emerging of this E6 is the duality where we decouple things this way, and we interpret this as the elementary blob E6. Is this clear? So we can make this a little bit more explicit again by taking our original collection of fields, where I, remember A is the SU2 index and I is the SU6. You see, this really suggests the way we should split things is to isolate an SU3 times SU3 times U1 subgroup of SU6 and think in terms of hypermultiplets that transform, so let's call this again M. Okay, how should I say it? I want to define a sort of an elementary object, which is the 3-puncture sphere with 2 big punctures and 1 small puncture. I want to think of this as a bifundamental in SU3 times SU3. So there are two SU3 symmetries. One, let's call this 1, and the other is called 2. And this symbol represents, let me not write the formulas for lack of time, that you should think of this as a symbolic representation of the Meller content of a hypermultiplet transform is in the fundamental of the 1, the anti-fundamental of the 2, but it doesn't matter because it's hypermultiplet, so it's if Q transform is fundamental and fundamental, Q tilde is the opposite, so it's just a matter of labeling. And this dot here represents the U1, which is the correct flavor assignment for a bifundamental hypermultiplet. And so now we want to interpret this picture in the standard perturbative frame as coming from taking this gadget and gauging the SU3. Okay? So this is just a rewriting of the original perturbative theory, where in the original way of thinking I had covariance under a full U6, and now I'm decomposing that U6 in terms of SU3 times SU3 times U1 times U1. And I think of each of these blobs as being a bifundamental hypermultiplet, and I'm gauging a common SU3, and this is just a rewriting of the original theory. Analogous to the one we did for SO8, but now we have to be a little bit more careful because we need to distinguish the U1. This clearly works, right? Because the originally I had U6, which is SU6 times U1, and then we are looking at an SU3 times SU3 times U1 times U1. So the SU6, as people pointed out, has rank 5, so rank 2 plus rank 2 plus 1. This is the composition of the flavored symmetry that has the correct rank, and that's a pictorial way to represent it. And so again, there is a duality transformation in which we exchange the role of equal punctures, and that's a standard duality we can understand in the old language. It's just a relabeling of the field theory content where we exchange the sign of the singlet mass. And then there is this new non-perturbative duality where we generate this E6 plus hyper. Okay? Questions about this? How am I doing with time? Okay, so before we vastly generalize this story, I want to say something about the Higgs branch. So one great check of these dualities is looking at how the Higgs branch behaves. And in fact, the Higgs branch is the same, doesn't depend on exact margin deformation. So the Higgs branch should be the same on either side of the duality. And okay, so there's a lot of things I have to say. I have to think of a way of say them efficiently. But we had this list of rank 1 F theory superconformal field theories. Remember, were A0, A1, A2, D4, E6, E7, and E8. Well, A0 has no flavored symmetry, so it has no X branches. Uninteresting for us. The others have X branch, as I told you quickly. This is clear from the F theory picture. This has D3 branes inside D7 branes, so the Higgs branch is the instant moduli space of a single instanton for the appropriate algebra. So for example, for A1, this is the Higgs branch, M Higgs should be identified with the one instanton. Well, I should say it's the centered instanton moduli space. The center of mass of the instanton doesn't matter. Of SU2. Now, those of you who know things will know that this is the same as C2 mod Z2. Now, C2 mod Z2, of course, is a simple space, so it has many, perhaps I should write here, has many representations, but the one that is relevant for us here is the following. C2 mod Z2 is also the same as the nilpotent orbit of the non-trivial nilpotent orbit of SL2. So let me explain this. In general, we have a complexified Lie algebra G. I'm going to soon drop the C. Everything that I'm going to do here is already complex number. So I look at the complexified Lie algebra. And of course, there's a complexified group. And so if I pick an element X in GC such that X to the n is equal to 0 for some n, that would be a nilpotent element. And there's a natural action of the group on the algebra. It's just the adjoint action. In terms of matrices, if you have an element of the algebra written as an n by n matrix, you act by conjugation with the element of the group to the left and with the inverse to the right. It's the usual way the Lie groups act on the Lie algebra. One sec. And so we let G of C act on X, and this is a certain nilpotent orbit. It's the orbit because as the whole group acts on this element, it generates an orbit, and this space is interesting. We are going to call it O sub X. Yes?
So you're taking x to the n in the universal envelope now?
In the universal, no, just in the algebra.
It's ad nilpotent.
Sorry?
It's ad nilpotent.
Yeah, sure. I mean, we're going to do an example in a minute. So let's do an example, because otherwise this is too abstract. Okay, so let's do our favorite example, which is SU2, or, well, in this complexified constant, the constant would be SL2. What's your favorite nilpotent element? Mine is this one. But clearly, all nilpotent elements for SL2 are the same up to conjugation. So now, how do I get the orbit? Well, I simply have to act with a general matrix A on X, and then A inverse, where A is an element of the SU of the SL2 gauge of the SL2 group. And what am I going to get? Well, obviously, I'm going to get elements of the form A, B, C, D. But this operation clearly preserves the fact that the determinant of this gadget is 0, and so necessarily you will find elements of this type, and moreover, since this operation preserves the fact that this is a Lie algebra M, it preserves the trace, also A plus D is equal to 0. Okay, it's clear that this is the general orbit of the nilpotent element. Or if I immediately solve, this would be A minus A, and so this would be BC plus A square equal to 0. Yes? Okay, those who know things will recognize that this is just a different way of writing C2 mod Z2. Well, why? Because I can solve for the relation. I can solve by saying that A is equal to some other letter. What could be a good letter? Big X times big Y, and then with an I perhaps, and then B would be equal to X squared and C would be equal to Y squared, and then this relation is automatically satisfied. And the X and Y parameterize C2, except not so fast, because it's clear that if I flip the sign of X and Y simultaneously, I get the same generators. And so this is just a way of saying that I have C2 mod Z2. Okay? So it's a famous fact that the moduli space of one SU2 instantons is either C2 mod Z2, if you want to give it the most explicit presentation, or you could say this fancy thing that it's the nilpotent orbit of SL2. In fact, in this case, it's a single non-trivial orbit, so we would say it's the minimal nilpotent orbit, or it's the maximal nilpotent orbit. Doesn't matter. It's the only nilpotent orbit of the group, apart from the trivial orbit where all elements are resulting 0 and that you're just sitting there forever. But the reason I went through this sort of somewhat pedantic exercise is that the story generalizes. And so there's a famous, beautiful statement that the one instanton moduli space, the centered one instanton moduli space for any simple gauge group G is the closure of the minimal nilpotent orbit of G. The closure is just a triviality. It has to do with the fact that here the 0 element was not included, but you want to include it, and that's just a singularity. Okay, so let's practice and let's explain minimal. Let's do SL3C. Well, now, actually, the story becomes a little bit more interesting. What are the nilpotent elements of SL3C? Well, there's a trivial one. Everything is 0. So X here is 0 on the nose. But then I could choose a Jordan block of this type, and then clearly this is nilpotent because X squared is equal to 0. But finally, there's also the possibility in which I could choose a Jordan block of this type, and then here X cubed is equal to 0. And I claim that up to conjugation, these are the only possibilities. And it's clear that these define different orbits. Okay, well, clear enough. The smaller orbits are included in the bigger one. Because if X squared is equal to 0, well, X cubed is also equal to 0. So there's sort of an inclusion of orbits of this kind. So very generally, we can represent orbits for SLN in terms of partitions of n. The partitions of n correspond to the dimension of the Jordan blocks. So in this case would be the 2, 1. In this case would be the 3, because it's a 3 by 3 Jordan blocks. In this case would be the 1, 1, 1. And there's a natural ordering of orbits, which is only a partial ordering in general, which is you say that an orbit is bigger than the other if the smaller one is included. Okay, so the statement here is that the moduli space of one instantons for SU3 is the minimal orbit. The minimal non-trivial one. This one is trivial, and the minimal one is this one. Okay? So in the case of SL3, or minimum for SL3, the dimension is actually, the complex dimension is 4, and the next orbit, this one, we have dimension 6. Okay, now for E6, which is the case of interest, of course I'm not going to be able to do this so easy with matrices, but the idea is very similar. You look for nilpotent conjugacy classes in E6, and you find the minimal non-trivial orbit. The minimal non-trivial orbit always corresponds to the highest root of the algebra. So another way in which you could interpret these nilpotent elements is to say that we have an embedding of SL2 into G, where SL2 I could have the usual EF H kind of triple, where H of E is equal to minus E, H of F is equal to plus F, or I mean, perhaps let's use more physics notation. I apologize. Let's call them this T plus, T minus, and T3. And so we have some mapping rho, and rho of T plus is an nilpotent element of G. And so I need to specify an embedding in the algebra, which in the case of SLN can be simply described by giving this Jordan-Blot decomposition. For exceptional algebra is a little bit more intricate, but it can be done. And the embedding that leads to the minimal orbit, apart from the trivial one, is the instanton moduli space. Okay. Now, incidentally, if you did the exercise that I suggested you do, you should have found that this was also the space that came from looking at the Higgs branch of this quiver. Okay, that's not a coincidence. And if you did the exercise for these ADE affine quivers, you would have found that the Higgs branch is always two-dimensional, and it's given by C2 mod ADE. In this case, for SL2, we're just modding out by Z2, which is the value group of SL2. Okay, so with this knowledge, we can now match the Higgs branch on the two sides of the Argyres-Seiberg duality. And okay, the detailed match is probably something I don't have time to do, but let's at least do a very elementary check. We should check whether the dimension works out. The complex dimension for all the example I had earlier, and in fact, for this purpose, let me also add G2, F4, E6, E7, and E8. These are not things that have a interpretation in terms of superconformal field theory, but I want to add them in the list because this is this famous Deligne series, the Deligne-Civitanovich series. It turns out the dimension of the minimal nilpotent orbit for algebras in this list is 2 times HV minus 1. So if we restrict to E6, we find that that is 2 times 12 minus 1 is 22. So let's compute the dimension of the Higgs branch on the exceptional side. Well, there's 22 that comes from E6. There is a free hyper, which is in the fundamental. So each hyper contributes 2, but there's 2 of them because in the fundamental representation of SU2. And then we need to do the symplectic quotient. And when we do the symplectic quotient, we need to impose a moment Mach condition. And then divide by the complexified gauge group. Each of them is worth the dimension of the group. So lo and behold, we find 20. On the gauge theory side, we have 6 hypermultiplets. So each hypermultiplet is going to be a factor of 2, and they are in the fundamental of SU3. And then we need to impose the F-term condition and divide by the conversified gauge group. Each of them is worth an 8, and so hopefully this will work. 6 times 3. Does it work? Great. So, but of course you can do a much more detailed check, and let me just sketch it very briefly. If you look at the, so we have, let's say that we parameterize the scalars alpha from 1 to 2 is this SU2 hat index I had earlier, and then the adjoint of E6 splits into the adjoint of SU6, the adjoint of, okay, I don't think I can actually do this in real time, and also I'm running out of time, so maybe this is not the best use of my time, but there is the adjoint of SU2, and finally the additional adjoint generators are something which is in the symmetric representation of SU6 and the fundamental of SU2, and then the F-term condition says that Z alpha beta plus V alpha V tilde beta symmetrized is 0, so we can eliminate the alpha beta everywhere, and now we need to form gauge invariant combination of these gadgets and impose, well, we have already imposed the F-term condition, which now we form gauge invariant combination of these gadgets, and we need to match them with the gauge invariant operator on the weakly coupled side. What are those? Those are easier to imagine. Those are the mesons and the baryons. We can form, let me write them this way, IJK. You can contract the color indices as a exercise. That's the unique thing that makes sense. These are the gauge invariant operators on the weakly coupled side. These are the ones on the strongly coupled side. And there's sort of, if you think a little bit for a minute, there's only one identification that makes sense. For example, the one identification that you like to do is MIJK would be identified, BIJK would be identified with YIJK contracted with V, etc. So I don't want to repeat the story now here, but you can perform this detailed check, and it works all the way through. The relations that you have on both sides, so these are complicated algebraic varieties where you have relations that come from, these objects obey various relations. For example, there's a relation that says that B times B tilde is equal to M cubed with a certain structure of indices. All the relations work out. I told you that there's a holomorphic symplectic form on the Higgs branch. That also works out. And so the Higgs branches really are the same. Okay, so questions about this before we now we do a vast generalization of the story.
We're in C2 mod ADE for the Higgs branch.
Yeah.
Do you also get that for the non-affine ADE quiver that has
the non-affine, the quiver is more complicated. I mean, I don't remember what's the result for U1, but in general you get something a little bit more involved. Okay, so what's the obvious generalization of this story? Well, first of all, let's go back to the trifundamental half hypermultiplets. So we discussed that this nice trifundamental gadget from which we can start to perform all sorts of gluing of this kind. And it's easy to check, although this was rather mysteriously missed in the old days, that any kind of graphs that you can draw, so let's be clear about what these graphs mean. Each node is a trifundamental half hypermultiplet, and each internal leg is an SU2 gauge group. The external legs are flavored symmetries. Is this clear? It's a somewhat compact notation for these generalized quiver diagrams. You can check that the beta function for the SU2 gauge group is 0 at each node. That's easy to see. So all of these theories are rather unusual set of quiver diagrams. They're all conformal. And it's not hard to argue that the conformal manifold is the complex structure moduli space of the obvious Riemann surface that you get by thickening this internal leg. So in this case, there is one circle, so it means it's genus 1, and 1, 2, 3, 4, 5 punctures, so this would be a torus with 5 punctures. How do we argue that? We argue that by performing this S-duality operation locally. Okay, so I can say that, for example, so assume that this gauge coupling is very, very weak, so that effectively this piece is decoupled. And then I perform the standard S-duality here. That will permute the flavored symmetries of this puncture by triality. And if I keep performing the operation locally, I will find that these distinct local triality operations actually do not commute with each other. And so I have to look at the maximal discrete group that contains all these subgroups, and that is the group that corresponds precisely to the correct identification of the complex structure moduli space of the 5 puncture torus, and so forth and so on. What is the physical interpretation of this? Well, as often in string theory or in advanced field theory, if you see an auxiliary object like this one, which is the conformal manifold of the theory, you should take it seriously and find a setting, a higher dimensional setting, where this is reified into an actual physical space. Okay? And so the idea is that this is an actual physical space in 6 dimensions. So that is the famous idea of, well, in simplicity, perhaps for this particular case was perhaps observed before, but Davide Gaiotto vastly generalized it. And so the idea is these are these SU2 trivalent quivers or sometimes called A1 quivers, arise from the 6-dimensional 2,0 superconformal field theory compactified on a Riemann surface C, which is precisely the surface that describes the conformal manifold. Okay, so this is the surface of genus G with n punctures, in this case G equal to 1, n equal to 5. This is sometimes also called as the UV curve to distinguish it from the IR curve, which is the Seiberg-Witten curve, which is a totally different beast. So the idea is you take the 6-dimensional superconformal field theory on such a Riemann surface. In order for the theory to partially preserve supersymmetry, you need to perform a topological twist. A topological twist, remember that the 2,0 theory has SO5 art symmetry. So we look for an SO2 times SO3. And we use this SO2 to twist the holonomy on the surface that preserves half of the supersymmetry. And so this partial twist of the 2,0 theory preserves n equal to 2 supersymmetry. And so we put the theory again on R31 times this Riemann surface with this twist. And then we flow. So the theory clearly, this Riemann surface has a size. So the theory in 4 dimensions is not conformal. But we flow to the infrared. And the infrared fixed point is the superconformal field theory, which is claimed to be identical to the generalized quiver theory that I drew now. And now this duality transformation becomes obvious. From the point of view of the bigger 6-dimensional theory, you just have this curve. The way you decide to describe the curve in terms of a pair of pairs decomposition is in your imagination, is how you decide to describe it. But from an intrinsic viewpoint, you just have this thing, which is the full complex curve. And so you have just one theory, in some sense, with different degeneration limits of the curve correspond to different weakly coupled description in terms of the quiver that you draw. Okay, so that's the basic idea of so-called class S. S is a silly name that means 6. You can further argue, somewhat tentatively and more precisely doing some holographic calculation, that in the process, the Kähler modulus of the curve is washed out, is irrelevant in the RG sense, and all that matters are the complex structure moduli of the curve. So the infrared fixed point only care about the complex structure of the curve. Well, but now, sorry, I should have been a little bit more precise. I don't know. Unfortunately, nobody told you very much. It should have been my job, but I had too many things to cover. Probably nobody told you too much about this 6-dimensional theory, except this basic representation theoretic facts that I told you. The theory has no marginal deformation, so it's a strongly coupled theory. And there is an ADE classification. Of 2-0 theories. So there's AN, DN greater or equal than 4, and E6, E7, E8. So when I told you that you perform this operation, well, this operation can be performed for any of these ADE theories, but the statement that you get these A1 quivers is pertains to the A1 theory. Okay, so this large class of 4-dimensional theory with SU2 gauge groups come from the compactification of the 2,0 theory of type A1. That can also be understood heuristically from another viewpoint. The circle compactification of 2,0 theory give you 5-dimensional super-Yang-Mills with maximum supersymmetry. And if you further down, go down 1 dimension, you get n equal to 2 vector multiplet with suitable boundary conditions. And so these very long tubes can be rather directly identified as weakly coupled gauge groups in 4 dimensions. But now, having understood A1, clearly we want to go on and do the game for all ADs, and in particular for the ANs with higher rank, N. And given what we have said so far, let me try to state this again. The 2,0 theory of type A1 on a 3-puncture sphere gives you this trifundamental half-hyper. I mean, of course, what I mean by the puncture in 6 dimension is a little delicate, right? What this really means, I need to impose suitable boundary conditions in 6 dimensions, and the boundary conditions are specified by a codimension 2 conformal defect. It's a defect that extends in the 4 directions of the 4-dimensional theory, but it's localized on the curve. And so it's, from the point of view of 6 dimension, this is an actual point in 6 dimension, which is extends in the other 4 directions, so there is an actual conformal boundary condition here. So this is a codimension 2 defect, which was known to exist. And by the way, I mean, this is not really much of a string theory at ASI, but this whole picture of 2,0 theory comes from taking superposition of M5 branes, and so you can understand this codimension 2 defect as an intersecting M5 brane. What about A2? What is the three-puncture sphere for A2, well, there is a very compelling guess. It's our friend, the E6 theory. You see, the idea is that we're associating to each puncture flavor groups of type SU2 for A1 and of type SU3 for A2. And E6, of course, contains an SU3 times SU3 times SU3 subgroup. So in this particular case, there is some sort of exception enhancement of SU3 cubed to E6, which will not happen in the next case. If I were to look at this three-puncture sphere for A3, I will find that the flavor group is SU4 cubed with no further enhancement. And so clearly now we can play the game for higher rank by gluing these blobs. In the case of E6, we already know quite a lot about it. So E6, in the case, there's a standard name for these blobs. They're collectively known as Tn, where T2 is the trifundamental SU2 half hyper. T3 is the E6 theory. T4, well, is some theory with SU4 cube gauge symmetry, but it had not appeared in the wild before Gaiotto's work. We have to accept it as a new elementary strongly coupled building block. And now by gluing these Tn theories, we can have fun and do all sorts of generalized quivers. So for example, you can check, and here again you have to know that the embedding index of SU3 into E6 is 1, and knowing that fact, you can now check that this gluing is perfectly conformal, because B1 is 2HV minus K over 2. Since we are gauging an SU3, this is 2 times 3. And K receives 2 contributions from here and from there. So it's a 3 plus 3 divided by 2 equals 0, as it should. Okay, I'm using the fact that the K of the E6 here was 3. And given that the embedding index of SU3 into SU6 is 1, K of the SU3 is still 3, but there's contribution from this side and that side, so it's 3 plus 3 divided by 2, and it works out. Final piece of things I need to tell you before I conclude, and I really need to tell you, otherwise the story is incomplete. These are the three-puncture spheres that correspond to maximal flavored symmetry. But we can now perform a very similar operation as the one I was performing earlier, in considering an embedding of SL2 into the SUN at each of the punctures that defines an nilpotent element and reduce the flavored symmetry accordingly. So the physical picture is we are moving on the Higgs branch. So we are choosing to give a VEV to the moment map operator that corresponds to one of these SUN symmetries in such a way that as we do that, only the commutant flavor algebra is preserved. The physical picture is one where you move on the Higgs branch, you flow to the infrared, throughout a bunch of decoupled Goldstone bosons, and what's left over is a superconformal field theory with less symmetry, with less flavored symmetry. And so what we really have is a set of Tn theories further labeled by a choice of 3 partitions that correspond to this operation I just mentioned. And finally, I need to state as a fact that if you choose the partition n-1, 1, this is the partition that corresponds not to the biggest orbit, but to the next to the biggest one. It's called a subregular orbit. And then the commutant in SUN is just U1. And so this is the case in which you are reducing the flavored symmetry of the puncture, which was an SUN, to a U1. And so the final claim is that that the TN theory, where we do nothing at two of the punctures, so these have full flavored symmetry, and then we do this particular n-1, 1 reduction at the third puncture so that we have U1. So this is a theory which has SUN times SUN times U1. They claim that this theory is the same as a bifundamental hypermultiplet. And so finally we recover as a corollary Argyres-Seiberg duality. Argyres-Seiberg duality is the statement that we are gluing in one frame. We have the 3T theory with 1 cube, 2, 1. That's the free hyper. In one frame we are gluing two of those. So this theory we were representing, I was doing earlier, by two big blobs. Those are SU3s. And one small blob, that's a U1. And so if I glue this theory in this pattern, that's a weakly coupled frame. And I should really interpret this as the 2,0 theory on a sphere with two maximal puncture and two U1 punctures. But then the same words that I had before apply. Intrinsically, this is just one theory, and it's up to me how I want to slice it. And so I should really be able to take the other decoupling limit, and in the other decoupling limit, I'm going to find my friend, the E6 theory. Okay, of course, there is infinitely more to say, but I'm afraid I'm out of time. And I really have 0 time, right?
-6.
Okay, so in my ambitious plans, this would have been the first half of my lectures where I was describing the general language and a little bit of the landscape of analytical theories, and then I would have introduced some more sophisticated modern tools, such as how you compute the superconformal index. And at least I have to say one thing. The fact that you get these theories from 6 dimensions and that there is this topological twist strongly suggests a kind of 2D 4D relation. There's a 6D framework in which you can either take the 2D manifold to be small and look at the 4D theory, or do vice versa, and for certain protected observables, the order of these two limits should not matter. And so, for example, if I consider, so let me end with this. If I consider the topology to be S4 times this UV curve, and I take the curve to be small, what do I have is I have one of these class S theories on the S4. So I'm computing the S4 partition function of this theory. But I could do things in the opposite order, and I first reduce on the S4, and I get some theory on the curve. And the idea is that this theory should depend on the conformal moduli of the curve and have good decomposition property under the degeneration limits of the curve. Well, and basically there's a compelling guess that you can make that in the case you start from the E1 theory, what you get is Liouville theory on this curve. And so this is a famous heuristic derivation of the Agt relation that says the S4 partition function of a one quiver theory is equal to a correlation function of Liouville on the curve. If you play the same game with S3 times S1, S3 times S1 is a four-dimensional version of the Witten index is what's called a superconformal index. And unlike the S4 partition function, which depends on the conformal moduli, it depends on the gauge couplings, the index does not. And so the statement is that, well, if you first use on the curve, you get the index of the theory labeled by the curve. But if I first use on this, I must get a topological quantum field theory defined on the curve, because the correlation function don't depend on the conformal moduli, and that conformity has been identified, and in certain special limits correspond to previously known topological quantum field theories, such, for example, the quantum deformed two-dimensional Yang-Mills theory. And this is just the beginning of a whole story where you can do now something even more sophisticated. You assign not just a number, a partition function to the theory, but a whole algebra. That is our work. You assign to the four-dimensional equal to superconformal field theory a whole vertex operator algebra,